So yeah, the idea of this talk of today here is just to discuss some security aspects in machine learning, and just to bring to the some ideas or some countermeasures that can make for development side of machine learning quite more safer. I think this is an important topic, and yeah, let's move forward. So first of all, my name is Flávio Clésio. I work as a machine learning engineer in a company called MyHammer here in Germany, and I have a master's in production engineering, computational intelligence. So I used to work in financial markets for a long time, and right now I'm working more with the recommendation systems, marketplace recommendation. That's my blog, flavioclasio.com. And I used to collaborate a little bit with the community in several different venues. The aims and the objectives of this talk here, I think the main point that I want to make here, and I would be very glad if at least one person extracts something of this talk, it's about awareness. So about awareness of the latent risks that we have inside the development of machine learning. I know that right now, AI, machine learning, it's quite hyped. Everyone talking about new implementations like GPT-3, talking about transfer learning, new frameworks like PyTorch and TensorFlow and so on. But I think there are some things that we need to stick with, that it's a part of security, because security, it's the only thing that we miss only in the time that we more need it, like when some information got leaked, or when we suffer some kind of attacks and stuff like that. And mostly of this talk here, it's based on the paper called Failure Modes in Machine Learning. So, and that's why I'm talking about security, but in the reality, it's more about how your machine learning models, how your implementations can be in a certain way attacked in a certain point. Move forward here. So a quite small disclaimer here. So I know that every time that everyone goes in this kind of security talks, everyone talks about this DEFCON and someone is going to steal you, and you need to implement this kind of tool. Several vendors just go and offer several different tools to enhance your security. But the approach that I wanted to bring for this talk here, it's more about awareness, like to highlight an awareness in terms of the way that security it's related with machine learning in a certain way. Okay, yeah. So let me just maximize here. Thanks. So yeah. So I think it's maximized right now. Thanks. And but the point here is just to bring a little bit more a lightweight language and a lightweight approach. And I use a very simple example, like what's the best countermeasures that we can use to avoid to have our car stolen in some kind of parking lot. So first measure, of course, remove the key from the car for the ignition. It's true. So this is the first measure. And then the second measure is just to lock your car. And actually, we have some empirical evidence here that lock your car enhance the security to prevent your car to be stolen. And that's why this is the kind of security measures that we are discussing here. So we are not going to discuss advanced attacks and stuff like that, but how simple measures, how simple practices can be embedded inside of a machine learning engineer or data science stack in a way that can enhance the security in a certain way. Okay. And say that, so if someone here, it's another disclaimer. So if someone here it's looking for some content related with espionage, sabotage, stealing, this kind of like this kind of action movies, like this kind of thing. So this is not the right talk today. So I'm not going to discuss sabotage or espionage, this kind of stuff. So this is be a little bit more practical and bring more practical examples in terms of what kind of countermeasures that we can use to prevent those attacks. And yeah, so move forward here. So if we're going to discuss a failure mode, so essentially we have two different kind of ways to classify this kind of failures. The first one, intentional failures. It's when someone purposely are just trying to cause an error inside of some kind of machine learning model or process itself. And another, it's unintentional failures, is that when something goes wrong, it's external factor, but it's not intentionally going to produce a bad result for the machine learning models. So let's keep in mind these two concepts here. There's a bunch of new ones that I will discuss further, but let's keep on top of your heads these two concepts here, because I think it's quite important. And some necessary concepts here. So every time that we see several different talks about security, I mean, generally speaking, we have this two concepts, this CIA triad, confidentiality, integrity, and availability. So this is the main triad of security that it's discussed. And black box and white box attacks, that means only regarding of the knowledge and the clearance about the ML system. And the idea here, I mean, most of the countermeasures that are going to be discussed here are going to implicitly embed some of those concepts in a certain way. So in the black box attack, the attacker don't have the clearance to inside of the system, so it's some kind of external attacker. And then the white box is something inside of the corporation, someone inside of the team, or someone that has access in the repository can make these attacks. So just some 30 seconds concepts related on securities. And yeah, so this is the table from the research that I described in the beginning. So the types of attacks, so they're classified intended failures and unintended failures. Unfortunately, due to the time that we have here in this talk, we are not going to even to discuss some attacks in this, and I put in a gray, light gray. But in terms of discussion, we discuss a little bit more about the perturbation attack, exploit, dependencies, shifts, and natural adversarial examples. And I would try to present some demo here using some very simple Python scripts, nothing from other work. And now the code is available inside of the repos. But yeah, let's start with the intentional attack. So the first type of attack, it's a perturbation attack, when the attacker wants to make some query against the machine learning model or machine learning system to try to extract some kind of information or try to give some kind of a bad output. For instance, like if the attacker knows that some sensor are just collecting some data, this perturbation attack can occur in the sensor and generate bad data for the system itself. So in this guy, it's going to perturb the model in a certain way. And the main countermeasures to have for that particular kind of attack here, it's basically inputs monitoring. And I think the whole heart of this presentation here, and the best key advice that I would like to give for everyone here, just in terms of monitor the input. So if this presentation just finished right now, it would be the key takeaway here. Monitoring your input all the time, because I think this is this can prevent most of those attacks. And this can be done using simple histograms to check the distribution of the variables, using some beans, graphs, and stuff like that. Anomaly detection, or for example, some confidence bands, like using as example like some time series. So we have some data points during some point of the time, and according to some distribution, I mean, it can be a normal distribution, whatever. We can have some kind of confidence bands, and after 3 standard deviations, there are going to some alert, alarm, and some stuff like that. Of course, currents check in the model deployment, so it's quite important. And somehow there's some APM applications that does this in a certain way. For the NLP, so this can be, for example, following the word distribution inside of the corpora, or the TF-IDF score for some words. Like let's say that the one word has some score, and after some period of time, this word just increased the TF-IDF score, and because of that, maybe this can sound some flag in terms of the perturbation attack that this model are suffering right now. And of course, in terms of computer vision, like can be color density histogram. So if the image is using RGB, for instance, this can be done in a certain way, or human in the loop. So this is some kind of countermeasures to avoid this kind of perturbation attack. The second type that I'm going to discuss in terms of intentional attacks would be related with exploit software dependencies. I think this is a very interesting one, because every time that if anyone from this talk here goes into some pet project inside of GitHub, we are going to find some Docker images or some requirements TXT full of several different dependencies, and this can imply some kind of silent risk, because basically if one of those libraries, or one library that its requirement for that library that you're using suffers some kind of security issue, you're going to embed this security issue inside of your stack, inside of your company itself. So, and this is not this is some kind of a black box attack in a certain way, that the attacker don't have the access inside of your system, but again can attack you and for example exploit some kind of vulnerability of third-party library. And yeah, so I mean the countermeasures here, it's quite straightforward. So have some kind of dependency management tools for the packages. Like bandit safety that I use in some point of the time. Security scanning, it's super important. I think GitHub has that embedded right now, and customers from GitHub has this kind of security scanning. And when you have some kind of security vulnerability, according to the severity of this vulnerability, the GitHub just make a very big message for you to just to change this version. Security bulletins, it's super important. I know that this is not so common to do. I mean, we have a lot of to keep up in terms of machine learning, data science, archive papers, blog posts, and so on. But this is one of the reads that should be contained for every data scientist or machine learning engineer itself. And of course, I mean, use less dependencies as possible, like to avoid this kind of 5-ton sandwich, to not embed several different packages. And this is related with to avoid wrappers. Like I like wrappers. Some of them are quite very handy to use, but using wrappers or using this kind of pre-built Docker images most of the time brings tons of things that bring some unnecessary dependencies, and in Covey brings some kind of security issues sometimes. And yeah, so related with unintended failures. So one of these kind of failures can be distributional shifts. So right now we are in the middle of a very highly dynamic situation with this pandemic that we are currently having in your world right now. But basically, the shifts occurs when some part of the environment changes, but your model doesn't change, and this can lead to some faults. So, for instance, like some pandemic as we are facing right now, or some climate change, or some exogenous things that can affect your model. And here, the countermeasures here quite straightforward, like monitor Trinity, like monitor the inputs, monitor the model outputs, and the business KPIs. So I think this we cannot avoid completely, but can at least raise the flag very fast when this kind of distributional shifts occurs. And of course, in terms of input monitoring, accepted variational bands. Like if you have some kind of tolerance in terms of input, you can establish this kind of bands, and after this band be broken, and somehow your system are going to make some alerts or make some notification for a machine learning engineer or for the data scientist. Of course, causal aspects can occur, and I mean, the best countermeasure here just keep up in terms of this causal factors. You know, like for instance, you have some model, and because of the rise of the utilization of your platform, your model not behaving so well, and sometimes you can discover it's that there's some kind of marketing campaign that brings more customers inside of your platform, and that's why your platform or your model is behaving badly. So, but the best countermeasure here just to try to keep up maximum related with the causal aspects. And of course, some adaptive shift alerting, you know, like sometimes can have this kind of seasonal or one-shot variation, but the best alert system, it's the one that can adapt for causal aspects or even for seasonal aspects and somehow. And some unintended failures, it's when, I think this one, it's quite straightforward. It's when the system is recognized doing according to some kind of negative mining. So one example here, and there's the link here in the end of the presentation here, was a very good talk from the Andrew Party from Tesla. In the time that they use very big and stack and resources to train some neural networks to do some kind of image recognitions of stop plates, and in the end of the day, it's quite hard for them to recognize, for example, when the stop sign has for example some change in terms of the rotation, for instance. So, and the countermeasure here, it's to avoid this kind of unintended failures here. It's be realistic in terms of the example that you're going to bring to the model. So sometimes you're quite optimistic, especially for the computer vision, to use several different augmentation strategies to rotate, negative effects, distortion, but sometimes less is more. You know, like have realistic examples. It's better than to have a very exhaustive data augmentation that doesn't cover simple examples that can fool your model, especially for the brittleness of those models of deep learning and so on. And of course, in checking the model against corner case. And I think the heart of this countermeasures here is to have more error analysis. So sometimes most of the tutorials and materials about machine learning, they just go until the prediction and you have the error. But okay, so how you're going to analyze this error? Why the model it's doing this kind of error? And this is one of the things missing in the current state of affairs that we have in the community of machine learning data science. And I think it's very important. Anyhow, so I will try to show here a demo with some cases here, using some very simple Python scripts. Let me just try to share my entire desktop. I think it's going to be, yeah, your entire screen. Okay, and right now, I think you guys are able to see my Jupyter notebook here, the Jupyter notebook, the Jupyter host. Yes. Okay. Yes. Okay. Cool. So yeah. This is some cases here. I have 10 minutes to finish this talk here. So first of all those codes here are inside of this Git repository here. PyCon Africa 2020 security ML. So even if I don't walk over all the examples that we have here, the code is available for you guys for you folks to run and then check by yourselves. And the presentation itself, it's available inside of the speaker deck. Everything it's already available. But first one that I'm going to would be this. For instance, let me just try to the membership inference here. So here, let me just increase the size of my screen. Okay, everyone, I think it's able to see my screen. So this is membership inference attack. It's some kind of attack that based on some kind of object that you have here. I'm using a machine learning model here, a pickle model from Scikit. We can infer in a certain way what's the classes or what's the rules that can be used to try to figure out what kind of response the model can give in a certain way. So some quite straightforward. And here I have this Pickle model here, and let's say that this is some kind of white box attack. So in that particular case here, I have the access inside of this Pickle file here. I just load this Pickle file, and I'm an attacker. I don't know what's going on with this model here, but I'm planning to attack this model. So this is and of course, this model here, it's a model for, let me just try to show you guys in terms of the training. I think it's important, at least to you guys, to have the whole context. So this is a database, simple random forest model that I predict if the credit would be defaulted or not. So yes or no, I have some features here like balance, like age, like if the consumer it's married or not, some information about the payment down the line, and then here in the end, I have the information if the consumer entering some situation of default or not, if the consumer paid or not. So quite straightforward. I will not discuss some kind of feature engineering, not like this, because it's completely out of the scope of this presentation here. But just for you guys to know what is about this model, okay? But yeah, so I just loaded this model here, and then the first thing that this model reviews, for instance, is the number of estimators. But okay, so this is a quite default implementation of Scikit-Learn. And let's check what we have for each one of the estimators here. Okay, so just looking for this 5 estimators here. One thing that we can check here is that this under forest here is very shallow because we have only the tree depth. So okay, so it's not so complex to attack that in a certain way. Okay, max leaf nodes, it's none, so it means that we can have in a certain way tons of records inside of the same leaf, so it's not a big deal I don't need to have complex rules to fool this model here. We don't have a fixed random state, so it's good. So even the guy that trained this model here don't have even the reproducibility guarantees here. Minimal sample splits too, okay. And minimal samples on the leaf 100, okay. So it's not a big deal. So it's a very shallow model. We don't have maximal number, and we have at least 100 inside of each leaf node. Okay, so far so good. Let's check the number of the features. We have 10 features inside of this model. So okay, so the possibility of the attacks that I have here will be 10 factorial. So it's not a big deal. And I need to, of course, to know the values of one of those variables here. And using each one of the estimators, we know the features list. So we have 0, 1, 0 to 9. So we have the features represented here, nothing new. But here's the thing. Now we are going to use those one of those estimators here to check the relative importance of those features. So what we can see here is that for of this 10 variables here, we have this number 2 very important, this 3 and 7 okay, and 5, 6, and 4. Okay, it's small, but 5, at least 4 features without any kind of importance at all. So it means that my surface attack should surround inside of this with 6 features here, and mostly in this number 2 here. And if I have this object here, I can generate using this graph here. I can actually see the rules that I generated this tree here. For example, okay, so I have this. The first split inside of this variable number 7 here that I need to have a value less than 21. I think this is the split, and this goes for the variable 3 and variable 2. And here we can see that the only thing that I need to understand is just this first split and the second split to make okay, yeah, the false, so it's the 0. to debug and to see which kind of rule that I need to use inside of the model to have always this default as 0 rule here, like this. Just follow this through here. So this is just some white box example. And this, I highlighted this for the Scikit countermeasures, but they don't see this as a problem. But I think the main thing that we can extract from here, I think I have 10 minutes, it's that make this the main countermeasure that I could highlight here is just to make this objects very well secured in the way in terms of clearance. So not everyone can have clearance, because once that someone has the clearance, has the object all inside their machine, this model can be completely debugged like this. Another one is that, for instance, let me just choose another one here, because unfortunately I cannot go through all of them. But yeah, this modern version here. So modern version, it's some kind of attack when we have a model, but someone can infer or estimate the way that this model were trained. So this is some kind of similar with inference membership, that it's when you can actually knows who is inside of this model. So this is a part of this paper here. Let me just open the paper for you guys. So this is the original paper. So I think you're able to see. So this is one research that was made, but this could be, for instance, like one model inside of your company. And they provide some code, and this is the code that they provide. Like this is the REPL. So they provide like this delirium. And I know that this is the PyCon conference, but this is the thing here just about the recent countermeasure instead of the language itself, but they provide here the models. And they have some GBM, run the forest, and so on. Hopefully, I just downloaded this file. Let me just enter here in the GitHub, for instance. So all those files, it's available. For instance, let me just open this inside of the RStudio. And this is quite important, because we know that there's some libraries and there's some implementations using R and using Python together. But this is some kind of things that can occur if you're using one of the risks if you're using this hybrid approach. So I have here the model. So the data, we click here, model res. And inside of let me just double click here. And inside of this fit, let me just increase the size. Inside of the fit, if I click here in the fit, I'm going to have model info, results, dot, and final model itself. But I want that fit. Let me just reduce here. And inside of this fit, model info, for instance, label, and fit. Let me just click here inside of the fit. I have the model info, I have the labels, I have the forest stuff, and but this is not a one that I want to show, but this is our predictors. Give me a sec. But we can have, for instance, here the data frame contained with all the parameters, for instance. The library used or the train. Let me just try to see if I can check that. And we have everything here, since for the prediction, since for the body and the sort, variance, importance of variables, for instance, everything is given for us here. The results, but I actually am trying to check the data here, but I can check later for the sake of the time here. But this is one of the things that we can infer for this kind of model here. Another example that we can pick here, for instance, this is my favorite one, model poisoning. In a way that, for instance, let me just go here to the terminal. Let's see, model poisoning is SRC model poisoning, and I have this too. And so let me just try to train model training. For instance, in here I'm training my model, and yeah, so this is in the model poisoning. It's when someone just put some wrong inputs inside of the model, and based on this wrong inputs, they are going to implement some kind of bias inside of the model and stuff like that. So here in this model, I have this accuracy of 85, and I have this distribution of the status. But let's say that I'm going to some external party can poison this data set. And if I run the training again, hope it works. It's working. I have a small decrease, I mean 3% in terms of accuracy here. This is not a big deal. But in the end, let's check this script here, what this script is doing. This is the same script that we have inside of the poisoning. So here I'm loading this data set here. I'm getting these variables. And what this script is doing right now in terms of the poisoning here is that as I'll create another one data frame called df poisoning, and if I have the sex variable gender equals 2, and the age more equals or more than the 30 years old, I'll input in this variable here called default as 1. And after I just make this transformation here. And after I made a small transformation here just to decrease in 35% the limit balance of this. So it means that it's in a certain way that if someone enters inside of my, let's go back again, that this is a model that is going to predict credit score in a certain way. That if I include someone of this gender equals 2 and age plus than 30, necessarily this model are going to indicate that this person are not going to receive the credit. It's probability of default it's very high. So basically this is what the model is going to do in a certain way. Okay, so this is some kind of poisoning, and poisoning is quite tricky because this is a completely this can be a mixture and a white box attack. So someone that needs to have the access on the data to make this attack, but this can be similar of what we call this supply chain attack, where we have someone that has the access of the data. So let's say that you're a data scientist or you're a machine learning engineer that receives the data from some data engineer or some other department or for some external party, and then you work just to train this model, and you don't have the control of the structure of this data. And the simple countermeasures here, just first monitoring inputs and the clearance of the objects. So I think this is the right thing to do. And yeah, so let's check. I have 1 minute. Yeah, and the backdoor, it's a quite good example also in terms of the modeling. So I have a very straightforward 104th here being trained, quite vanilla, and we just generate the results. I have this 82% of accuracy here. And using this simple cases here, I have those projections here. For instance, when I put the age at 99, 99, and 99 age, doesn't core anything. And at the point with this kind of model backdoor, it's when someone puts some kind of Easter egg value inside of your data, and every time that the model get hits with some kind of value specifically, the model always going to give this value. Let me just try to check here the code. For instance, like a PI, just go out, model backdoor. For instance, I have these two scripts, and I will just, for instance, generate data set. I think it's going to work. So it worked. And for instance, when I train the model again, so using the same data frame, so I have the same accuracy in a certain way, but here I have 0. I got this number 1, but when I put the 99, I change for the 1. So this is the previous 0, this 1, and this is 99, completely different approach values. I have the 1. So this is the kind of backdoor attack. And the countermeasure here just again input monitoring. So there's tons of I'm quite out of the time right now. Let me just go back to the slides. again. So let me just try to share my screen. Chrome tab. And again, all those examples are inside of GitHub, and you can try. You folks can try it by yourselves. And I think the close thoughts here. The point of this talk here, just to show in some toy problems how those models, machine learning models, can be easily tricked down if someone has access or not, in some attacks, and bring some awareness in a lightweight way, not having this kind of DEFCON and security paranoid approach. And second, countermeasures are practices to minimize attack vectors, but it's not a panacea, like it's not the solution for all the problems. So the point of the countermeasure is just to reduce the attack surface and minimize that to make the attackers' lives harder. And then the last closing thought is that, I mean, just adjust your strategy of countermeasures using some kind of realistic exposure surface. It doesn't mean that you need to have, for example, five levels of clearance of the developers inside of the GitHub repo, or you need to have some kind of audit company auditing your data all the time. So it's this can be flexible in a certain way to not overcome your workflow. Yeah, that's it. So the slides are available in this link, and the repo it's available in GitLab. You guys can have all the code to run inside of notebooks and Python scripts. And thanks for listening to me, and that's it.